Okay, so this is advanced physiology. This is topic 6, which is cardiovascular system. This is the first lecture. So call this, the notes are called topic 6 part 1, and this is the first lecture in that from this set of notes. Okay, so so this slide kind of illustrates the basic problem of a diffusion that's faced by multicellular organisms. Okay, so first of all, so supposing we're a single-celled organism, shown here. So a single-celled organism, zooming in on the membrane here. So this is intracellular space, extracellular space. So this is the external, fluid that it's floating in, swimming around in, and they need to basically bring nutrients in to the cell from the outside. So nutrients from outside to in, and then they need to take waste and move them from inside the cell to outside. And for a single-celled organism, for transporting these things, the easiest way to do it is just to rely on diffusion. And basically, diffusion is governed by Fick's law. So the flux is equal to permeability times area times, delta concentration divided by delta x with the membrane. And so, the main thing that basically drives diffusion is concentration difference. The bigger the concentration difference, the more rapidly diffusion occurs. And so, if you're floating around, if you're a cell floating around in this external fluid, the concentration of waste is relatively low compared to what it is in a cell. So there's a pretty big concentration difference, high inside the cell, low outside. So it's relatively easy to get fast diffusion and get rid of your waste just through diffusion that way. And then hopefully, if you're swimming around in a nice juicy medium, there is lots of nutrients externally and not much inside, so you can get nutrients in by diffusion pretty readily too. But if you're a multicellular organism, so say you're this guy here, and let's say that the cells on the outside of the organism are fine, right? They basically have the same advantages that this cell here does. But if you're the cell here on the inside, you don't have any direct contact really with the outside fluid. And then, so let's say you just build like a canal, sort of like this, into the interior of the organism like that. And maybe that'll solve your problem, but it won't really, because, so this is the external fluid, this is the central cell. So the nutrients might be pretty high up here, out here. But as that fluid kind of flows in to the center of the organism, right, the cells along the way are withdrawing nutrients. So by the time that the fluid gets to this central cell, there's actually not much nutrients here. Delta C isn't very big, and diffusion is going to be really slow. Likewise, there aren't many waste materials out here in the external fluid, but this waste cell, isn't in contact directly with this, and so, it puts out its waste. And then all the cells along here are also putting out their waste. So the waste concentration in this fluid is pretty high, and you're not going to be able to move things out very effectively by diffusion. The waste out because there's high concentration in the external fluid. So diffusion by itself won't really work. You can't just hope that the fluid will flow in and out the way you want. So instead, what most multicellular organisms do that are of any significant size is that they construct a system for basically moving the external, like the fluid that's outside the organism, and moving that fluid into the center of the organism. They don't move that fluid directly in, but what they do, they create a circulatory system that takes blood, brings it to the surface, and then then it moves nutrients into the blood, moves waste out, and that's you have it to be directly in contact with the good fluid in the external environment. So lots of nutrients, not much waste. You can get good exchange, and then you take that you move the blood that now has lots of nutrients that have moved in and the waste that have gotten rid of, and you bring it around to the cells so that the blood, when it arrives here at the cells, is basically like the external fluid, lots of nutrients, not much waste. The cell can then, put its, take the high level of nutrients and take it in, get rid of the waste pretty easily. And then the blood then circulates back around and does the exchange again. So in this diagram, it's showing the blood exchanging, doing with the surface here to get nutrients in and get rid of waste. But in more complex organisms, of course, we do those. We have separate systems for bringing in nutrients. So the gastrointestinal system brings in nutrients, and then other systems for getting rid of waste. Mostly the urinary system, right? But the blood basically acts to bring fluid, like the external fluid, into the middle of the body. Okay. So the cardiovascular, but the key is you got to keep this stuff flowing. You got to keep the blood flowing around. Keep the blood flowing around the body all the time to make this system work. If it just stands still, then this cell is going to start, basically it's going to suck all the nutrients out. It's going to fill it up with waste, and then it's going to not be able to exchange anymore. So you've got to keep that blood flowing. And so one key concept for cardiovascular physiology is that the rate at which cells can exchange, bring nutrients in, get rid of waste, is proportional to the rate of blood flow. The faster the blood flows past a cell, the more exchange it can do, the more materials it can bring in, and the more waste it can get rid of. And you can see that when you look at how blood flow is distributed among the different organs in the body. So at rest, you can see that here's how the blood is distributed. So in general, the more demanding, the more metabolically active organs get more blood supply. So the brain, gets, it's quite a small organ in terms of weight, but it gets a lot of blood supply relative to its size. Same with the kidneys and the heart, especially those three. Skeletal muscle gets a decent amount, but not that much at rest, really, relative to its size. And then I think the really clear illustration here is during high demand exercise, the body redirects a lot of blood to the skeletal muscle because the metabolic activity of those cells goes up. So those cells are going to need a lot more nutrients. They're going to put out a lot more waste. And so to deal with that, the body gives those tissues, the skeletal muscle, a lot more blood flow. Okay, so the more exchange of cells needs to do, the more blood flow it's going to need. Okay, so what determines where blood flows, how much blood flows in the body? So here is sort of just a really simple drawing I put together to illustrate how basically fluid flow is controlled. Okay, so here what we have here are two chambers with fluid in them connected by a vessel, a tube with resistance R. We want to measure the flow through that tube. The symbol for flow is Q. And then the thing that drives the flow of fluid through this vessel is pressure that's applied on the two chambers. So there's pressure here. There's a pump that's creating pressure in this chamber. We'll call it that P1. And there's a pump that's creating pressure over here. We'll call that P2. And so we want to ask the question, how big is Q? Given that we know, say given a certain P1, P2, and R, what's the flow going to be? And the basic equation for that is actually is something we've encountered already. Actually, as an equation that we used for the electrophysiology section. So we said that the flow of current is equal to the voltage divided by the resistance. So the voltage is kind of the driving force, and the resistance is, the resistance to flow. So I equals VR for electricity. This is Ohm's law. So you can actually take the same law and just do what I call the hydraulic version. And it looks like this. Q is equal to delta P over R. Okay, so bigger pressure difference gives you more flow. Bigger resistance gives you less flow, right? So R is in the denominator. So we usually will define flow as being a positive value. So we'll say, we'll put the bigger number to the left minus the smaller number to the right. So we'll say that P1 is big, P2 is small. For our, we'll just say we'll arrange our situation so that P1 is the bigger one, P2 is the smaller one. So Q would be equal to P1 minus P2 over R. And that measures the flow from this side here, where P1, which is the bigger pressure, over here to P2, which is the smaller pressure. Okay? Okay, so that's how, and this equation basically applies to any system where fluid is flowing through pressurized pipes. So applying to that to the circulatory system. So here is a slightly more realistic depiction of the circulatory system and the different components of it. So this is the heart. So left side, right side. The left ventricle is a pump that puts pressure on blood and sends it out into the aorta, then flows through systemic organs. There's a certain amount of resistance through here, especially in this region. And then the blood returns back to the right atrium, and then goes through the lungs, but we're kind of ignoring that. For the sake of this analysis, we're looking just at the flow from the left ventricle through the body to the right atrium. That's going to be what we're mostly going to focus on. So the higher pressure is over here at the left ventricle, right? So the average pressure of blood in the aorta is 85 millimeters mercury. That's the average across systole and diastole. So when the blood's squeezing really hard, it goes up above that. When the blood's when the heart's relaxed, it's down below that. And this is the average pressure. So we'll kind of talk about how the pressure goes up and down during the cycle. But this is just the average pressure. If you took if you averaged systolic and diastolic, you'd come up with this pressure, which is what's called mean arterial pressure. So 85 millimeters mercury is kind of a typical value. Okay, so that's just so we can sort of compare, put this into the analogy that we made before. We'll call that P1. And then P2 would be the pressure at the other end, where the blood is being received, and so that would be the pressure basically in the vena cava or the right atrium. And it turns out that pressure is really very close to zero. So the delta P in our equation is going to be so if this is P2, so call this P2. So delta P is P1 minus P2, and it's MAP minus 0. So basically the driving pressure on blood in the body is essentially mean arterial pressure, because the venous pressure is usually about 0. Okay. Sorry, let me fix my handwriting a little bit. There we go. Okay, and And then you have, the blood flowing through the system. You have aorta, smaller arteries, and capillaries, veins. And so in this region, especially the capillaries and especially as we'll see, the arterioles right before the capillaries is where most of the resistance of the system comes from. So, there's basically, but the whole system creates a certain amount of resistance to flow, and so that the total resistance throughout the entire system is called total peripheral resistance, or TPR. Okay, and so then we can just do what I'm going to call Ohm's law for the cardiovascular, so the cardiovascular version. And what we're going to want to be able to basically, we're going to use this equation to tell us how much blood is going to flow through the system. And so that volume of blood is called cardiac output. So cardiac output is the volume of blood that flows through the cardiovascular system, like per unit time. Usually it's like liters per minute or milliliters per minute. So cardiac output is equal to mean arterial pressure divided by TPR. Okay, which is right. This is the same equation basically as this one. Flow is equal to delta P over R. So delta P is mean arterial pressure. R is TPR. So cardiac output is equal to mean arterial pressure divided by TPR. And then rearranging this, you can also say mean arterial pressure is equal to cardiac output times T. Oops. Sorry. TPR, or TPR is equal to mean arterial pressure divided by cardiac output, right? I mean, all those are just rearrangements of the same equation. And so we're going to be spending a lot of time thinking about how exactly, so cardiac output is equal to pressure divided by resistance. So, how do these three variables actually relate to one another? So, like, if pressure goes up, does cardiac output go up? Well, it does, but what if pressure goes up and TPR goes up, right? If they both go up, then maybe cardiac output won't change. And what actually happens? How do these three actually relate to one another? We'll talk about that later. It's kind of a complicated question. But first I want to just talk about the factors that, essentially I want to understand blood flow. And I want to understand blood flow, I want to understand the factors that determine what the pressure is and what the resistance is, right? If we can understand the factors that determine pressure and the factors that determine resistance, then we will have basically understood the factors that determine cardiac output. Okay, so let's start with talking about resistance. Okay, basically thinking about the vessels. So the first thing is that we'd like to say, let's measure TPR. What's the total peripheral resistance? It turns out that measuring that in terms of actual physical resistance, the way you could measure it with a pipe, if you had a pipe, you could measure the resistance in some standardized unit. Not really feasible for the cardiovascular system. But when physiologists want to talk about how much resistance there is, what they do is they use this equation: TPR equals MAP over cardiac output. And so, because it's fairly easy to measure these two things, mean arterial pressure you can just get from a blood pressure cuff, and cardiac output, there's some not easy. You have to kind of do you do an ultrasound probe to measure the flow out of the heart and that kind of thing, but you can do it relatively, it's a pretty common thing to be able to measure. So if you want to measure someone's resistance, all you need to do is get their pressure and their cardiac output, and then you have their resistance, and is just pressure, the pressure divided by the cardiac output is their resistance. The units are kind of weird, so let me just introduce you to sort of a way that physiologists have dealt with the problem of, like, you can't really measure resistance directly. So if we know that TPR is equal to MAP over CO, what we can do is we can make a new unit, basically create a unit for TPR. So where it's basically millimeters mercury, which is the unit of pressure, divided by milliliters per second, which is the unit of cardiac output, and you call that peripheral resistance unit. So 1 PRU is equal to 1 millimeter mercury per milliliters per second. And so if you measure pressure and cardiac output, so typical mean arterial pressure is about, we said like 85 millimeters mercury. And it turns out typical, so cardiac output is about approximately 85 milliliters per second. So typical TPR is about 1 PRU. Okay, so measured in PRUs, the typical value is 1. That's sort of like an average value across people, different people, in different conditions. But sort of, I think that would basically be like at rest. And then they've sort of defined, if you get really stressed and your resistance goes up, or if you get really relaxed and your resistance goes down, TPR can vary from about, say, 0.2 to 4. That's kind of a normal range. So, and that goes to show that, so going from 1 to 0.2, that's dropping by a factor of 5. Going from 1 to 4, that's going up by a factor of 4. So that's a pretty wide range that our vascular system can change the resistance of the system, right? So what is it that causes TPR to vary, though? Like, what are the factors that go into the resistance of the vascular system? Okay. So there are basically, let's see. So factors involved in resistance of vessels. So there are kind of two factors that go in. So the first one is basically the resistance factors that determine the resistance of a single vessel. So we need to sort of understand the things that determine for a single vessel how much resistance it has. But then the second thing is the resistance of a circuit of vessels. Okay, because of course, in this image we've drawn, like, the blood flow is kind of going through basically one tube through the body back to the right atrium. But of course, in the body, that's not what happens, right? The blood comes out of the aorta, and it goes all kinds of different places, right? At the same time, basically in parallel. So, we may Sorry, let me go back here. We may be able to, predict sort of the factors that determine resistance of one vessel somewhere in here. If you can think about what the resistance of a single vessel, but it's not obvious how changing the resistance of one vessel will change the total resistance of the system, and that's what ultimately determines CPR. So we're going to want to talk about both. Okay, so for a single vessel, we need to understand the forces that act on the blood as it flows through a vessel. Okay, so this picture up here, where's my cursor? Okay, this picture up here shows a vessel, and this is sort of a diagram showing what blood kind of acts like as it goes through that vessel. And so to understand what's happening here, let's think about like the forces that are acting on the blood. Okay, so there are basically two forces. So first, you've got pressure pushing on the blood, trying to basically push the blood through the vessel this way. Okay, so that's one force. But the other force that you get is friction that the wall places on the blood. So the basically, blood, of course, like any fluid, is just a bunch of molecules that are moving more or less randomly, and they're being pushed by pressure in this general direction. But as they're moving, they're moving along this way, and they're doing, that's whatever. You're just kind of moving randomly, getting pushed along. But imagine if you're up by the wall, and you're moving along, and you kind of keep bumping into the wall, and you're losing energy as you go. Every time you bump into the wall, you lose energy. So the blood that's near the wall loses energy because of basically colliding with the wall. It's sort of what we refer to as the friction of the contact between the blood and the wall. The nearer you are to the wall, the more friction you're going to experience. So the guys over here experience a lot of friction. They're kind of slowed down by it a lot. The guys in the middle don't actually experience much friction and can move pretty smoothly through. And so what you get is this pattern where you have like these central layers of blood that are moving pretty rapidly, and then the further out you go, the more slowly the layers move. This is called laminar flow. And a lot of fluids flow, as they flow through tubes, flow in this way. Okay? And the laminar nature of blood, and the fact that like the blood near the wall experiences more friction than the blood in the center, explains a lot about the resistance that a vessel places on blood flow. So in fact, we can calculate the resistance of a vessel. There's a law called Poiseuille's law, I think it's called. And pronounce it's a really difficult word for an American. But so if you want to calculate the resistance of a single vessel, the equation is R is equal to 8 times nu, we'll see what that means in a second, times L divided by pi times R to the 4th, where nu is blood viscosity, L is vessel length, and R is vessel diameter. Okay, and this is a law that actually applies to any pipe, and it's any hydraulic system. So if this is our pipe, we've got fluid flowing through it this way. The resistance of this pipe, it depends on the length of the pipe, So, and it makes sense, right? A longer pipe would have more total, would have more total resistance, harder to get fluid through a longer pipe than a shorter pipe. So L is up here in the numerator. Okay, viscosity of the fluid. Why is that a factor in? Well, so when a fluid flows, in this laminar fashion, you get these kind of layers of fluid that are flowing, and this one's flowing fast, and they're flowing more progressively slower. So these layers kind of end up flowing past one another. This one in the center flowing faster, and it's having to sort of move past the one above it, and so on and so on. So in any fluid, when two layers are flowing past one another, there's a certain amount of stickiness, right? So and you can imagine like a real gooey fluid, like jelly. If you try to move the top layer of jelly, it's going to kind of stick to the layers beneath it. And so this stickiness of the different layers of a fluid is called viscosity. It basically says, how fast can I move the one layer without, past another layer, and how much force do I have to apply to move a layer past another layer. And if a fluid is very viscous, it means it's hard to move one layer past another layer. Okay, so the more viscous a fluid is, the harder it is for these layers to flow past one another, and so the harder it's going to be to get the fluid through the tube. So that's why you get viscosity in the numerator. More viscosity means more resistance. But then the big factor is the radius of the vessel. Sorry, this should be error. So vessel diameter should be vessel radius. Apologies. And vessel radius is down here in the denominator, so bigger vessel means less resistance, right? That makes sense. So like if the vessel is wider, there's less resistance. Narrower means more resistance. But the big thing to notice here is that radius is raised to the power of 4. Okay, so vessel radius has a huge impact on resistance, and you can kind of see that here in this diagram here. So if you have 3 tubes of diameter 1, 2, and 4, the rate of flow goes up like vastly more as you so you have a factor of 4 increase in diameter, but a factor of 256 increase in how much goes through it. And that's because in a large vessel there are a lot of layers of the fluid that are far away from the wall, and these flow quite efficiently. In a small vessel, pretty much all the fluid is in contact, very near to the wall, and a lot of viscosity or a lot of friction from that wall, contact with the wall. Okay, so radius has a really big impact on flow. It's the biggest impact on the resistance of a vessel, and therefore the flow through that vessel. And we'll see that the main way that the body changes basically the resistance of a vessel is by changing the radius of that vessel. You can constrict a vessel and make its resistance go way up, or dilate a vessel. So you constrict it and it's got a lot of resistance, dilate it and it doesn't have much resistance. Fourth power effect there. Okay, so that's one. So there, that's so for the single vessel, it's basically Poiseuille's law. R is equal to 8 nu L divided by pi r to the 4th. Okay. Okay. So then we have to think about, well, now what do we do? What happens to resistance when you have multiple vessels? Okay. So and that depends on how the vessels are arranged. And so if you have different vessels arranged one after another in a line like this is called in series, so that the flow has to go from this chamber to chamber 1 to chamber 2 to chamber 3, and has to pass through R1, R2, and R3 in order to get through. This is called series resistance, and in that case you get a simple sum. So the total resistance of this series of of vessels is, so the total is equal to simply the sum of the individual resistances. You should figure out R1, figure out R2, figure out R3, and the resistance of the total is just the sum of the three. Versus if you instead arranged your system so that the three vessels were what's called in parallel, so that blood can come in and can go through any one of the paths to make it to the other side. So up here we have to get through each of the vessels to get to the other side. Here you can choose which vessel you want to go through to get to the other side. This is called being in parallel. And to help understand the math of this one, so we'll define the resistance R1, R2, R3, and we'll also define what's called G, the conductance, as being just 1 over R. So basically a big resistance means low conductance. A small r, small resistance, would be a big conductance. Okay, so G is just the opposite of resistance. It's how easily blood can flow through. So in this case, if you have three vessels, 1, 2, and 3, the math is, this is the complicated way to express it, 1 over R total equals basically the reciprocals add, and then you have to flip it over at the end. I think the much more intuitive way to understand it is that here the conductances add, which means that so the more vessels you have, the bigger the total conductance becomes. In other words, and so RT is just 1 over GT. So the bigger GT becomes, the lower R becomes. The more vessels you have in parallel, the lower the total resistance. More vessels in parallel makes the total resistance actually lower. Okay? What do we see in the body? Which one do we see? Well, if you look at kind of a whole body level, it's basically a parallel arrangement. Okay, so blood comes out of the left ventricle through the aorta, and then it goes through the major arteries, and the major arteries branch off to a bunch of different places, and blood can go through any of these paths to get back to the right ventricle. So at this sort of whole body level, the vessels are arranged basically in parallel, and blood can and each of these branches doesn't really add much to the total resistance, because if there's a lot of resistance here, the blood can just go through here instead. And so, the more paths there are, the lower the total resistance. So on a whole body level, the different paths that blood can flow basically add in this sort of inverse way, and so the more paths there are, the less the total resistance. One of the sort of most important consequences of that is that if you think about the blood coming, where's my cursor go? Coming out here of the aorta, so it flows, different ways. So like as the blood's flowing down here, some blood will be given off and flow this way. But the blood, so the blood going to one organ, it doesn't actually affect the pressure in the blood going down to other organs. Okay. Now, so let's compare that. So if like say this was like, the heart and like liver and gut, and then back to the heart. So if the blood had to go for the liver and then the gut and then the heart before it got back to back to the heart. So let's say there's lots of pressure here. As you flow through each of these guys, the pressure is going to be dropping and dropping and dropping, so that the pressure might be high here, but the pressure when it gets to the gut isn't so high anymore. Pressure sort of drops progressively. It goes through a system like this. Whereas in a parallel arrangement, the blood is at a certain pressure at this point. When some blood goes off here or here or here, it actually doesn't really affect the pressure that's left down here. So basically, the take-home message of that is that each branch of of the artery to sorry, I'm losing my dang cursor. Each branch that goes to each major organ has about the same pressure. Okay, the pressure is about the same no matter supplying each organ in the body. Although the one thing that can actually cause the pressure to be quite different is gravity. So when you're standing, the organs up here actually have less pressure in the blood than the organs down here because of gravity. But the arrangement of the vessels doesn't actually affect it. So gravity can affect it, but the branches going off to different organs doesn't really affect it. Okay, so that's kind of one major consequence of this parallel arrangement in the body. But there is some place where you do face sort of a series effect in with the blood flow, and it's basically when you get down to kind of the tissue level. So there's arteries that branch off to major, lots of arteries that branch off to each of the major vessels or organs. But once we get here and look at the blood flow as it flows through an organ, we basically start getting into, this is basically sort of a series phenomenon of blood flow. So at the tissue level, all blood has to go through arterioles, and this is actually they're going to be the major sort of bottleneck, and then capillaries and venules, kind of bigger little veins, and then veins. So this is an arteriole and a venule. And you actually find that there aren't really a whole lot of arterioles. There aren't a lot of different arterioles for blood to go through once it gets close to tissues. And so arterioles especially become kind of the limiting point for blood flow, and the resistance of arterioles can be quite have big effects on the total resistance of the blood flowing through a certain organ, and can actually make it so that blood flow through that organ drops quite a bit, or goes up. So if the arterioles constrict, it can cause blood flow to drop. If arterioles dilate, it can cause blood flow to increase. Okay, so I'm going to stop this recording, and I'll finish the lecture in the second recording.